So the main idea behind Genie is to learn a generative interactive environment from videos alone, such that if you take a single image, you can kind of step to it and interact with it like it's a real environment. So we basically can take in sequences of frames, plug them into a VQ model so that we can discretize our video frames, and then the model can predict tokens. Essentially, we're learning over this large, very diverse data set with many different kinds of environments, dynamics, but we wanted to try to learn this sort of compressed version of what changed so that it'll be useful for the model to predict next frames. So the reason I would say that it's consistent is because it's just very helpful for the model to learn this consistent action space across different environments so that it can predict next frames. When we're generating next frames, the objects that are further away are moving more slowly than objects that are closer. And this is a sort of effect that you would often see in games such that you can kind of simulate depth. It's something that we also have it, like when we observe things moving, we see things moving slowly when they're further away. So yeah, the model learned that. The thing that I liked the most about Genie was you can actually interact with the model. So you're not just generating something, like you're actually able to take actions and change the generations that you see. And if you don't like them, you can rewind and create different sort of generations.
The Brave Search API brings affordable developer access to an independent index of over 20 billion web pages. What sets it apart? Well, it's built from scratch, without big tech biases, powered by real anonymized human page visits to filter out data and refreshed daily with tens of millions of new pages. Perfect for AI model training and retrieval augmented generation, the Brave Search API offers ethical data sourcing at developer-friendly prices that scale with your business. Whether you're working on language models or information retrieval systems, Brave offers representative datasets and up-to-date information affordably. We'll get started with 2,000 free queries monthly at brave.com/API. Now, Ashley, you were one of the authors of this Genie paper.
Yeah.
Can you tell us about it?
Yeah, sure. So the main idea behind Genie is to learn a generative interactive environment from videos alone, such that if you take a single image, you can kind of step to it and interact with it like it's a real environment.
Amazing. So can you tell us about the architecture?
Yeah. So basically, the main thing that we do here is that we're going to try to learn a latent action model. So typically, if you're familiar with like world models, you usually need something like actions in order to interact with the environments. But we learn a latent action model that basically allows us to control these environments. So that's one main component. And then we have a dynamics model that takes in these latent actions and predicts the next frames. We also have a video tokenizer to represent the frames that the model can predict.
Oh, interesting. So the video tokenizer, if I understand correctly, that's trained first. And that's,
yeah. Mm-hmm. Yeah, exactly. So we basically can take in sequences of frames, plug them into a VQ model, if you're familiar with that, so that we can discretize our video frames, and then the model can predict tokens now. So we're going to be predicting this discretized version of our frames.
That makes sense. So this VQ VAE, so that kind of creates a code book. And I'm guessing the input images were quite a high resolution, right?
Yeah, I think it was 90 by 160 were our frame, the size of our frames. And then we could basically take those into patches, put them into the model and predict the tokens essentially.
Fascinating. Okay, so you can take frames in. So let's say we got a data set of like videos of platform games, and then we do this video tokenizer, and then there's this latent action model. So there were no actions in the video.
Yeah, exactly. Yeah. So we first learned the tokenizer. Our latent action model actually operates on raw pixels. So we're not using that tokenizer for training the latent action model.
Okay, that's so interesting. So we can infer the actions, and then the actions and the video tokens go into a dynamics model which produces the output video.
Yeah, exactly.
And I guess the action model fascinates me the most. So I think in Genie, did you folks constrain it to 8 actions?
Yeah, exactly. Yeah, mainly because we wanted something that we could also interact with, because that was kind of one of the I guess, one of the best evaluation tools was actually stepping into our model and playing it ourselves. And so if we had a large latent action space, it would be difficult for us to play it. So we reduced it down to 8 actions. And the other thing is that we wanted to compress it such that it would be useful for the model to make next frame predictions. So having this sort of small code book allowed it to kind of encode what's the most important thing that represented what changed between scenes.
One thing that really puzzled me, and it's amazing that it works so well, is that even over successive frames, the actions were kind of reasonable and consistent.
Yeah.
Yeah. Why was that?
This, I would say, surprised many people in the team as well. I always believed it could work, but not everyone did. But I would say the main reason is because essentially we're learning over this large, very diverse data set with many different kinds of environments, dynamics. But we wanted to try to learn this sort of compressed version of what changed so that it'll be useful for the model to predict next frames. And so the reason I would say that it's consistent is because it's just very helpful for the model to learn this consistent action space across different environments so that it can predict next frames.
Yeah, that's so interesting. So when we've trained this architecture then, it could be set up so that a human could actually play it as if it were a game. So it's almost like a game engine, but the game is a kind of, it's coming from the imagination of the model.
Yeah, exactly. And the imagination of the user as well, because you can generate the images that you give to it, you can sketch them. So yeah, it's basically learning to generate these from these initial prompt frames.
Yeah, and I think you can even use a text description as well. How does that work? So do you have a text to image model and then that just becomes an input into the video decode?
Yeah, exactly. We just take an off-the-shelf text to image model and generate an image, then plug it into the model. So we don't input text to it directly though.
That's so cool. So I could sketch like, a platform game or something, and then I can put it into Genie, and then I could have a gamepad or something, and then I could play the platform game from that sketch as if it were a game engine. Yeah,
exactly. If your drawing skills are... Yeah, but I drew a thing, and I'm not a very good, I guess, drawer, and it still was, we were able to control that. So yeah.
Yeah, that's so cool. I mean, how creative do you because it's learning this kind of world model essentially, and how much can it generalize out of the distribution of what it was trained on?
Obviously, it's going to work better on the in-distribution examples, but the images that we were generating, we were trying to make them give it sort of prompts that would make it look a little bit more like the kinds of things we were training on. But yeah, like we mentioned, sketches worked too. So I think as long as you had something that looked like you could control it, then it could be able to control it. It didn't always control it, but a lot of the times it did.
Very cool. So I read the paper and it said there was a metric for the action model and also the video model, which was based on fidelity. Like how do those metrics work?
Yeah, so we had FID, which is a sort of common metric for measuring video quality. So this is saying, like, if you roll out the generations of your model, how well does it match the distribution of the things you trained with? That measured, the fidelity of the videos, but it doesn't really measure controllability very easily. So another thing that we did was we measured what we called PS&R diff. So PS&R is another metric for measuring the fidelity of images being generated. But we essentially wanted to see if we plugged in our ground truth latent actions and compared that to random latent actions that were inferred by the model, what was the difference between those two things? Because we wanted the latent actions inferred by the model to actually generate the proper generations, and random latent actions essentially to not necessarily lead to the proper next frame. So if you compare these things, we wanted to see what the difference was.
Yeah, super cool. So if I understand correctly, at the moment, it's based on a fixed number of frames. Mm-hmm. But in the future, could we make a streaming version? Or maybe it already is streaming and I just didn't understand.
It might not get that interesting if you rolled it out forever. But yeah, exactly. You can just truncate the number of frames that you're plugging into it or generating or that sort of thing. But you could, we played it for more than 16 frames, which it was trained on.
That's really good because I'm quite interested in the concept of video generation. Mm. And it feels like that's the hardest problem, like in the AI space right now, because it's so difficult. Like, how close do you think we are to just being able to generate videos just continuously?
I think in this Genie work that we had here, I wouldn't say that it would be able to do it that well, but I think there's improvements for it. We've already seen, I think, in the past couple of months, many different works putting out, long generations, but consistency is a problem. So maybe if you move outside of a scene, you would have forgotten the kinds of things that you've seen. I don't think we're that far from it, though. The field is moving very fast. I would say maybe this year or within a year or something, we would be able to stream, but it depends on how long you would want to stream it for, I guess.
Yeah, I'm really worried that my job will be automated by streaming video generative models.
Oh, I highly doubt it. People, you still want to interact with people and have these kind of conversations. It's not going to be interesting to watch AI generated interviews, I think.
There was a mention of emergent abilities in the paper. So the examples were 3D understanding and parallax and deforming objects and so on. That was a really interesting phenomenon. I mean, what do you think about that?
Yeah, it was cool because I think it was one of those things that we noticed and we're like, oh my God, it can actually do this. Like, for example, in the parallax example we have in the paper, you can see when we're generating next frames, the objects that are further away are moving more slowly than objects that are closer. And this is a sort of effect that you would often see in games such that you can kind of simulate depth. It's something that we also have it, like when we observe things moving, we see things moving slowly when they're further away. So yeah, the model learned that.
Very cool.
Yeah.
Now, the model was 11 billion parameters. And when I say the model, I mean like all of Genie, so all of the models put together.
Yeah.
That doesn't actually seem super big. And you did some scaling analysis as well, where you looked at what happens when the models change in size. Can you tell us about that?
Yeah, so we had a couple of different experiments to measure both like the model size or how the model performed when we scaled the model size as well as the batch size. So like you mentioned, we ended up scaling it to 11 billion parameters, had a batch size of 512. I think probably the fidelity of the model got better as we scaled it. We also saw the latent actions performing much better, like controllability happening better when you scaled the model to 11 billion parameters.
Yeah, and it was just like a real smooth scale, wasn't it? It was just, there was a commensurate increase in the size of the model.
Yeah, it was a really pretty one. I think Jake from the team spent a lot of time getting this figure. So yeah, kudos to him.
How much data was it trained on?
So the data set, an original data set had about 300,000 hours, but we spent a lot of time filtering this down. So we all got together and kind of labeled the data set and ended up filtering it to around 30,000 hours of footage, essentially.
Very cool. And if I understand, it was like 10-second clips at 10 frames a second. And I think it was quite low resolution frames, right?
Yeah, exactly. Yeah.
Okay, very cool. And you folks used an ST, or a spatial temporal transformer. Mm-hmm. Tell us about that, and why is that better than something like VIT? So
essentially in a VIT, what you would do is you would take patches from an image and then plug that into a transformer and then predict, I guess, try to reconstruct these patches or the next patches in our case. But the problem was that we're trying to, learn a representation that captures things that change across time. And so we wanted to have this sort of temporal component so that we can see like how we can model things that are moving. So that's the temporal part. The spatial part is what's coming from the images. The other thing that we did was because we don't want to actually have a transformer that's having to attend across all of these different frames, we only had it attend to one token across time, so that it was basically scaling linearly rather than quadratically.
Oh, cool. And there was a causal mask as well, right? So there's like there's like one little a 1x1 slice going back 4 frames.
Yeah, exactly.
Yeah. So that's frames, that would.
Yeah.
Yeah, but if I understand correctly, so is that helps you capture like the time dynamics, but then there's the spatial slice as well. So it's almost like a T-shape where you've got spatial information, then you've got like a causal slice going in the time dimension.
I see. Yeah, I haven't actually thought about what the shape looks like, but I think that makes sense there. Yeah.
Very, very interesting. Now, I mean, something I've been thinking about is you can almost think of this is a form of gamification in general. So, language models are a form of gamification, but it doesn't feel like a game because we're typing and we're interacting with it in a weird way. Mm-hmm. But this feels like a much better form of gamification. And it might be the trend of more AI models that we create, that there's a much tighter feedback loop with how we interact with them.
Yeah, that's a good point. I think the thing that we liked, or the thing that I liked the most about Genie was you can actually interact with the model. So you're not just generating something, like you're actually able to, take actions and change the generations that you see. And if you don't like them, you can rewind and create different sort of generations.
The main application for this, I mean, obviously this is great being able to generate games, but robotics is the next frontier, right? And the problem with robotics is that we just don't have, we don't have labeled data with actions in it. But you could take this model and in the paper, that's what you folks did. You actually trained a reinforcement learning policy based on the inferred actions from Genie.
Yeah, so we trained a behavioral cloning policy. So we don't have rewards, but we basically train an agent to imitate from unseen videos using the latent actions that we learned. Yeah.
So how well did that work?
Yeah, I think it worked pretty well. There have already been prior works on doing like imitation from observation, but what we wanted to see essentially was that if we took latent actions learned from our platformers data set, if we can actually use them to label unseen videos and then get an agent to imitate from that. So basically, if you took if you learned the latent actions, so you're going to learn a policy of your latent actions, but you can't just take that and plug that into the environment. We have to map those to real actions. It was a little bit difficult to actually get the agent to learn on the fly to map latent actions to real ones, but we could take some expert labeled data, included actions, and learn a mapping that way. And that worked pretty well. Yeah.
Yeah, that's really interesting because, the latent actions, we don't know exactly what the actions are. So we get some experts to make the mapping and then we can actually test it on like a real world, problem.
Yeah, so in this case, we took expert data that had like in this state, you took this action, and then we could do a mapping ourselves. So we didn't actually have people directly mapping that real actions to the latent ones.
Oh, very cool. Very cool. So what would it look like if we, let's say we had loads and loads of video data from YouTube or something like that, and we trained a robotics model? I guess I'm thinking with the video games, 8 actions seems quite appropriate, but I mean, what would happen if we had a massive action space? Like, would it collapse in some way, or do you think it would scale up?
Yeah, I think that, we did have a few experiments where we saw how the model changed as we increased the action space. And I would say that the fidelity of the generations would get better. So, you can imagine the latent actions are trying to tell you what's going to happen in the next frame. So as you have more latent actions, then it's going to be able to control that better. I think in terms of mapping that to the real environment, that's the part where it's going to get a little bit more difficult, I think. Like, how do you map this giant latent action space to the real actions that you can take? Robotics actions are continuous, so that's another thing that we would have to figure out. Like, how do you map those? I think maybe you could discretize them or that sort of thing. But we saw that in the paper. I think we also used like 8 actions for the robotics example. It worked for a robot arm. Or if you were doing like maybe first person perspective, and you would learn like go forward, move left, move right, rotate, whatever. That's still a small action space. But yeah, it's a good question.
Yeah. What would a foundation model look like for robotics?
So I think, we've seen people like, I think at 1X, they're actually working on doing this sort of foundational model for robotics. They actually open source Genie, which is quite cool. Chelsea Finn's lab is also learning, like they have this giant database coming from many different labs, which I think is quite cool. So like basically having taking data from many different sources, because it's very difficult, I think, with robotics. Like a lot of the videos on the internet wouldn't necessarily map directly to what a robot needs to see. Like you might see like some first person things that you can map, but it doesn't show you like how to move a robot arm or interact with necessarily objects. So I think, trying to train over all sources of data, not necessarily just things on the internet, but also other robotics, and sort of collaborating across that space. I still think, maybe you would want to use sensor data for that too, because there's certain things that you can't get just from observations, like haptics and that sort of thing.
There was also mention of, let me just get the reference to this. Mask-GPT was used as part of the decoder model. I'm not familiar with that. How does that work? Yeah,
so the way this works is that it takes in, you take in masked tokens like you would see in something like BERT, and then you're trying to basically predict next tokens given those masked frames, I would say. And so I guess the main benefit from Mask-GPT versus something like if you're doing autoregressive generations of your tokens, is that you can generate them in parallel. So you can like imagine you have like a frame of tokens. You can mask or you can unmask multiple tokens at a time and keep the ones that you're most confident with, and then condition on those and try to unmask the rest. So it gives you a big speed advantage essentially.
Really cool. Yeah. So at the moment, the performance of this, I think you folks said was about 1 frame a second. So it's not quite fast enough yet. How could we optimize this? So I would say, trying to get inference speed was one of the also important things. We're interacting with the model ourselves. But doing things like, we're using Mask-GPT, which doesn't really
I've never seen like a distillation approach for Mask-GPT, but you can imagine that you could try to do that. So try to distill into a faster model, do some sort of other efficiency things like using like bfloat 16, for example. But I think distillation is a good thing to try out here.
Very cool. Tell me more about your background. What are your research interests?
Yeah, so my main research has actually been in getting agents to learn from videos. So I come from a reinforcement learning background. My PhD was in reinforcement learning, but I basically got a little bit annoyed with having to always come up with a reward function or even like the environments. So I became interested in how we can actually take agents into like show them videos from the internet essentially, and then get them to learn from that rather than me having to like show them the reward or that sort of thing.
Very cool. I mean, what do you think is the roadmap for agents? Just in general. So we're talking about having LLM agents, for example. I mean, what's the cash value of agents?
Yeah, I think it's one of the questions that we always see. Like, where does the data come from? For example, like you're having to put agents in the real world. It can be very expensive. I think learning from videos. This is why this is how I ended up in Genie as well. I was doing imitation from observation, and then I think it was Jack who was like, no, let's learn environments themselves. And so I think learning from all the data that you can essentially for agents is really going to help them scale. Figuring out how we can represent rewards and learn from humans as well. Trying to make them more efficient, which is also always, of course, the case. But yeah.
Very cool. And what research are you most excited about at the moment outside of Genie?
Yeah. So video generation, I think that it's interesting because I've kind of shifted a little bit from doing reinforcement learning into doing these video generation techniques. So yeah, this is the thing I think I've been really excited about these days. It feels new, but it's not that new because I was always working on training agents for videos, but now it's like, oh, let me see what video generation is like.
And what do you think the biggest challenge is with video generation?
Like we mentioned before, I think consistency across frames is important. Also, like if you're doing text-generated videos, getting your generations to follow the text prompts that you put in. But also, controllable video generation is the thing I guess I'm most excited about these days. So trying to find out ways that you can control them on a frame-by-frame basis, which is what we did in Genie. But I think it could be interesting for other models as well.
With the multi-agent stuff, do you think we will design systems with enough autonomy that they can like run without close human supervision?
Why not? Eventually. I mean, it depends on the time frame and depends on the systems, I guess, that you would want. I think for things like self-driving cars, we've already seen Waymo driving on the street without human intervention. I'm a little bit afraid to get into them, but they seem to work. I think, it depends on how safe these systems are. If it's something that you can just put on like in any system and it wouldn't harm anyone, then, roll it out and see what happens, I guess. Yeah.
Cool. And what's it like working at DeepMind?
Well, I've actually shifted to Runway now. So,
you're right. Sorry, I should have known that.
Yeah, well, that's all right. It's very recent.
I'm so sorry. Gen 3 is incredible.
Yeah, it's great.
I used it on my Murray Shanahan interview to generate a Shoggoth typing on a laptop. It was just first time. It was amazing.
It is really good. Yeah, it's really good. DeepMind was great though. But I really just wanted to go to a startup and see what it was like. And like I mentioned, I'm very into video generation these days. So.
Oh, that's so cool. So there was a huge jump in capabilities with V3.
Yeah.
do you think it's just going to continue to get better?
I can imagine so, yeah. I joined the week they put out Gen 3. So it's like a very fun time to join. I wasn't expecting it. I didn't know about it before I joined. So that was actually quite surprising. But we've seen like the pace that video generation models have been improving is like kind of crazy. Like I think like Sora just came out in February, right? And since then we've just seen so many more and more, advancements happening in the field. So.
Wow. I mean, at the moment, there's been this kind of race to build bigger models with more data. So there's a commensurate kind of relationship between capabilities and model size and data size. Do you think we might discover something that really improves the efficiency of the model?
Yeah, I think so. I think another thing to look into is not just to try to scale these models, but to maybe build upon the ones that already exist so that you don't have to keep running these giant experiments and finding out ways to improve it just by doing things like classifier-free guidance or like distillation and that sort of thing. Control net is another way you can improve your the generations from your model and fine-tune it and that sort of thing once the model already exists.
Amazing. Well, Ashley, thank you so much for being on MLST. I really appreciate it.
Thank you as well. It's nice to chat.